Every detail in this story comes from real scientific research and observation. Somewhere in the constellation Orion, a star may already be dead. Its light is still arriving. It has been arriving for 548 years. In the winter of 2019, astronomers watched it grow dim, faster and darker than anything in the historical record. For weeks, no one knew why. Some said the star was choking on its own dust. Some said its surface was cooling in patches the size of continents. Some said this was the beginning of the end. This star is larger than the orbit of Jupiter. If it replaced the Sun, its outer edge would reach past the asteroid belt, and Earth would already be inside it. And yet it is not solid. It is not smooth. It boils. Vast columns of gas rise and fall across its surface, each one wider than the distance from Earth to the Sun. Deep inside, in a core smaller than the Earth itself, the physics of matter is running out of options. Layer by layer, element by element, this star has been burning through the periodic table. Hydrogen, helium, carbon, neon, oxygen, silicon. Each stage burns faster than the one before it. The final stage, when it comes, will take less than 1 day. When the core finally collapses, it will happen in less time than it takes to draw a breath. A wave of nearly weightless particles called neutrinos will pour out first, moving almost at the speed of light, arriving at Earth hours before anything else. Then, eventually, the visible light, the actual explosion, will follow, and for weeks this star could be as bright as the full moon. It could be visible in broad daylight. Ancient civilizations recorded events like this before in the years 1054, 1572, and 1604. New stars appearing where nothing had been, gods and omens written into the sky. No one alive today has ever seen a star die this close. But somewhere in Orion, the countdown may have already started centuries ago, and the light simply hasn't finished the trip. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. The star, the numbers, and the history in this story are real, drawn from current astrophysics and centuries of recorded observation. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. For over 500 years, a single point of reddish light has burned in the shoulder of the constellation Orion, and for most of human history, no one knew what it truly was. It sits roughly 548 light-years from Earth, a distance so vast that the light reaching a telescope tonight left that star centuries before telescopes existed. It is a red supergiant, one of the largest known types of star, with a radius so extreme that if placed at the center of the solar system, its surface would extend out past the orbit of Mars and possibly to Jupiter itself. In recent years, this star has become the focus of intense scientific attention because its size, its instability, and its age all point toward the same likely conclusion. It is nearing the end of its life, and no one knows exactly when that end will come. Long before any of this was understood in scientific terms, the star had a name and a place in the sky that people across the world had already claimed as their own. In the night sky, the constellation Orion is one of the easiest patterns to find, a rough hourglass of bright stars anchored by 3 in a perfect row, the belt. Above the belt, on the upper left, sits a star with a noticeably reddish color, distinct from the blue-white of its neighbors. The ancient Greeks called this constellation the Hunter, a giant figure raising a club or a bow, forever chasing prey across the heavens. The reddish star at his shoulder eventually took the name Betelgeuse, a name whose origins trace back through medieval Arabic astronomy, likely meaning something close to the hand or the armpit of the Great One, a phrase describing its position within the figure rather than the star itself. Orion was not only a Greek invention. Long before the Greeks gave it that name, ancient Egyptian astronomers associated this same pattern of stars with Osiris, the god of the afterlife and rebirth, and some researchers have proposed, based on alignments studied at Giza, that the 3 pyramids may correspond to the 3 stars of Orion's belt, though this remains a debated interpretation rather than settled fact. In ancient Babylon, the same stars were known as a different figure entirely, a shepherd or a sheep, recorded on clay tablets that predate Greek astronomy by well over 1,000 years. Across cultures separated by oceans and centuries, with no contact between them, people looked at the same arrangement of stars and consistently saw a figure, armed, standing, watching. On the opposite side of the world, in the oral traditions of Aboriginal Australian sky watchers, the stars now known as Orion were also read as a hunter figure, sometimes described as a young man pursued across the sky, with the belt stars and their surrounding pattern interpreted through stories passed down for tens of thousands of years, some of the oldest continuously maintained astronomical traditions on Earth. In some of these traditions, the reddish tint of Betelgeuse itself was noted specifically, described in ways that suggest careful, repeated observation of its color over generations, long before anyone had a word for a red supergiant. This detail matters because it means human beings have been watching this star and noticing its distinct color for far longer than recorded written history extends. In ancient China, the same stretch of sky was mapped under an entirely different system, one built around 28 lunar lodges rather than Greek constellations. The stars of Orion's belt and shoulders fell within a region called Shen, recorded in astronomical texts and oracle bone inscriptions dating back more than 3,000 years. Chinese court astronomers were meticulous record keepers, tracking the position and behavior of stars for administrative and calendrical purposes, and their surviving records would later prove valuable to modern astronomers studying long-term stellar behavior, including sudden bright new stars appearing in the sky, events now understood to be supernovae. In the Norse and Finnish traditions of Northern Europe, the same stars were sometimes read as a tool rather than a hunter, a scythe, or a distaff, evidence that the same pattern of light was reinterpreted endlessly depending on the tools and labor most familiar to the people looking up. What stands out across nearly all of these traditions, separated by geography, language, and thousands of years, is that the reddish star was rarely ignored. Observers repeatedly distinguished it from the surrounding blue-white stars of Orion, particularly from Rigel, the bright blue-white star anchoring the opposite corner of the constellation. The contrast between the two, one star burning blue-hot, the other a deep orange-red, is visible even without any instrument, a naked-eye clue to a difference in temperature and life stage that would not be scientifically explained for thousands of years after it was first noticed. By the time European astronomers began cataloging the night sky with early instruments, Betelgeuse had already been assigned its place, listed among the brightest stars visible from Earth and given the designation Alpha Orionis. In 1603, the German astronomer Johann Bayer published a star atlas called the Uranometria, introducing a systematic naming convention still in use today. Within each constellation, stars would be labeled with Greek letters, roughly according to brightness, starting with Alpha for the brightest. Betelgeuse, as the most prominent star within the boundaries Bayer assigned to Orion, became Alpha Orionis under this system, even though, confusingly, it is not always the single brightest point of light in the constellation, since its slow variability occasionally lets its neighbor Rigel briefly outshine it. But listing a star's position is different from understanding what it is. For centuries, astronomers had no way to know that this point of reddish light was not simply a distant sun similar to their own, but something almost incomprehensibly larger, sitting in one of the final chapters of its life. Islamic astronomers of the medieval period preserved and extended this observational record with remarkable precision. In the 10th century, the Persian astronomer al-Sufi compiled the Book of Fixed Stars, a detailed catalog that recorded the positions, brightness, and even the colors of stars visible to the naked eye, building directly on the earlier Greek catalog of Ptolemy, while correcting and refining it through fresh observation. It was through translations and transliterations of Arabic astronomical texts, centuries later, that the star's modern name entered European languages, a name that scholars still debate the precise origin of, with proposed roots meaning the hand, the shoulder, or the armpit of the great figure the star sits within. In the Vedic astronomical traditions of ancient India, the stars of Orion were mapped as mstriga, a deer or antelope, pursued across the sky by a hunter represented by the star Sirius, a mythological chase echoing, almost precisely, the same predator and prey relationship found independently in Greek and Aboriginal Australian traditions. Some versions of the story identify the deer figure with Prajapati, a creator deity, wounded and fleeing across the heavens with the arrow that struck him represented by the 3 stars of Orion's belt, across at least 4 independent civilizations, separated by mountains, oceans, and millennia. The same visual pattern of stars produced strikingly similar stories of pursuit, a coincidence researchers attribute not to shared contact, but to the simple, universal shape the stars themselves happen to form. In the 15th century, the astronomer and ruler Ulu Beg, grandson of the conqueror Timur, built one of the most advanced observatories of the medieval world at Samarkand in present-day Uzbekistan, equipped with a giant stone sextant more than 30 meters in radius, sunk partly into a hillside to measure the positions of stars and planets with an accuracy that would not be surpassed in that region for generations. Ulu Beg's resulting star catalog, completed around 1437, listed the positions of more than 1,000 stars, including the stars of Orion, cross-checked and refined against the earlier work of Ptolemy and al-Sufi. This chain of catalogs passed from Greek to Persian to Central Asian astronomers and eventually into Latin translations used in Europe, represents an unbroken thread of careful observation of the exact same points of light, stretching across more than 15 centuries and at least 4 major civilizations, long before anyone understood what those points of light actually were. By the late 18th century, the astronomer William Herschel, working from England and already known for discovering the planet Uranus, undertook a separate and painstaking project cataloging the colors of stars visible to the naked eye at a time when the physical cause of stellar color was still entirely unknown. Herschel noted Betelgeuse specifically as one of the most distinctly reddish-orange stars in the northern sky, a simple visual observation that, more than a century later, would be confirmed by spectroscopy to reflect a genuine and measurable difference in surface temperature. It was Herschel's son, John, continuing and extending his father's meticulous observational habits, who would go on to notice that this particular star's brightness was not merely reddish, but restless. A meaningful step toward understanding came in 1836, when the astronomer John Herschel, son of the more famous William Herschel, began systematically tracking the brightness of Betelgeuse over time and noticed something unusual. The star was not constant. Its brightness rose and fell in irregular cycles, sometimes over months, sometimes over years, a behavior almost never seen this dramatically in an ordinary star. Herschel's observations were among the first scientific evidence that Betelgeuse was not simply large and red, but actively unstable, its outer layers shifting in ways that changed how much light reached Earth. Later in the 19th century, astronomers developed a new method for understanding stars entirely, not by their position or brightness alone, but by splitting their light into a spectrum, a rainbow of individual wavelengths that reveals a star's temperature and chemical composition. At the Harvard College Observatory, a team of researchers led initially by Edward Pickering and carried forward largely through the meticulous work of astronomer Annie Jump Cannon, cataloged the spectra of hundreds of thousands of stars, sorting them into a classification system still used by astronomers today. Under this system, Betelgeuse was classified as a cool M-type star, among the coolest and reddest stellar surfaces known, a designation confirming what careful observers had already suspected simply by looking at its color for thousands of years. This classification revealed something that seemed at first contradictory. A star's color is a direct indicator of its surface temperature. Blue-white stars like Rigel burn at surface temperatures above 10,000 degrees Celsius, while a star glowing reddish-orange like Betelgeuse sits far cooler, somewhere in the range of 3,000 to 3,500 degrees Celsius, actually cooler than the surface of the sun itself. And yet Betelgeuse is, by almost any measure, far brighter than the sun, radiating roughly 100,000 times more total energy into space. The explanation lies not in temperature, but in surface area. A star's total energy output depends on both how hot its surface is and how much surface it has, and Betelgeuse's surface, stretched across a radius hundreds of times larger than the sun's, is so vast that even at a relatively cool temperature, its sheer size allows it to radiate an almost unimaginable quantity of energy every second. Recognizing that Betelgeuse's brightness was not fixed but constantly shifting, astronomers eventually organized systematic, long-term monitoring efforts to track it. Beginning in 1911, the American Association of Variable Star Observers, a network combining professional astronomers with thousands of trained amateur observers around the world, began collecting nightly brightness measurements of stars like Betelgeuse, creating a continuous observational record that in some cases now spans more than a century without interruption. This long unbroken data set would later prove essential because when Betelgeuse's brightness dropped sharply and unexpectedly in late 2019, astronomers were able to compare the event immediately against more than 100 years of prior data and recognize, within weeks, that nothing quite like it had been recorded before. The scientific story of Betelgeuse only truly began in the early 20th century, when astronomers developed the tools to measure not just where stars are, but what they are made of, how large they are, and how they change over time. Even the best telescopes of that era faced a fundamental problem. Stars are so distant that through any ordinary lens, they appear only as points of light with no visible disk or surface, no matter how powerful the magnification. Measuring the actual physical size of a star required an entirely different approach, one based not on magnifying the light, but on analyzing the way light waves interfere with one another. In 1920, physicist Albert Michelson, already known for his precise measurements of the speed of light, worked with astronomer Francis Pease to attach a specially designed instrument to the 100-inch Hooker telescope at Mount Wilson Observatory in California. The device used two mirrors mounted on a long beam, spaced apart to capture light from a star at two slightly different points, then combined that light to produce an interference pattern, a series of light and dark bands whose spacing depended directly on the star's angular size in the sky. It was an elegant solution to an apparently impossible problem, using the wave nature of light itself as a measuring tool, precise enough to detect a star's diameter across hundreds of light years of empty space. The star chosen for the very first successful measurement of this kind was Betelgeuse, selected in part because its position in the sky and its unusual brightness made it a practical target. The result, published in December 1920, was startling even to the scientists making it. The star's angular diameter implied a physical size hundreds of times larger than the Sun, a figure so large that some astronomers initially treated it with caution, uncertain whether the technique itself might be flawed. Subsequent measurements, using increasingly refined instruments across the following decades, repeatedly confirmed the original finding, and in some cases suggested the star was even larger than first calculated. Even after Betelgeuse's physical size had been measured, one basic question remained surprisingly difficult to pin down: exactly how far away it actually is. The standard method astronomers use to measure stellar distance is parallax, observing a star from two opposite points in Earth's orbit around the Sun, 6 months apart, and measuring the tiny apparent shift in its position against more distant background stars, the same effect that makes a nearby object seem to shift when viewed first with one eye, then the other. For most stars, this method is remarkably reliable. For Betelgeuse, it is not, because the star's surface is constantly boiling and shifting, its apparent center of light moving unpredictably from measurement to measurement, introducing errors that ordinary stars simply do not produce. Early parallax measurements, taken through the 20th century, placed Betelgeuse at distances ranging anywhere from about 400 to more than 800 light-years from Earth, a frustratingly wide margin for a star otherwise studied so closely. Even the European Space Agency's Hipparcos satellite, launched in 1989 specifically to measure stellar positions with unprecedented precision, struggled to produce a fully reliable figure for this particular star. It was not until a detailed 2020 reanalysis, combining data from multiple observational techniques and accounting directly for the star's surface instability, that astronomers converged on a refined estimate of approximately 548 light-years, now the figure most widely accepted in current research, though even this number carries a margin of uncertainty of several dozen light-years in either direction. That single measurement, made using nothing more advanced than mirrors, light, and careful mathematics, marked the beginning of a century of increasingly precise study, one that continues actively today, using space telescopes and ground-based observatories capable of resolving structural detail on the surface of a star that is, even now, more than 500 light-years away. Modern instruments, including the Atacama Large Millimeter Array in Chile and the Hubble Space Telescope, have gone further still, producing actual images of Betelgeuse's surface, faint and blurred, but real, showing patches of varying brightness that shift and change over months and years. Today, professional observatories and the same kind of trained amateur network that began in 1911 continue to monitor Betelgeuse on a near-nightly basis, whenever Orion is visible above the horizon, feeding data into shared international archives that any researcher can access. Every measurement adds to a data set, now well over a century long, one detailed enough to catch subtle changes in brightness within days of when they begin, rather than months or years later. It is this continuous vigilance that allowed astronomers in the closing weeks of 2019 to recognize almost immediately that something genuinely unusual was underway. What those instruments have found in the centuries since Pease and Michelson's first measurement is a star unlike almost anything else visible from Earth, unstable, enormous beyond ordinary intuition, and running out of time in a way that can now be measured, tracked, and in the next part of this story, explained in careful physical detail, layer by layer, down to the core where its ending is already being written. Understanding the history of how Betelgeuse was found, named, and measured is only the beginning. To understand what is actually happening inside this star and why astronomers now watch it so closely, it helps to look past the mythology entirely and examine the object itself, layer by layer, exactly as modern instruments have mapped it. A red supergiant like Betelgeuse is not a single uniform ball of gas. It is closer to a structure of nested layers, each behaving differently, held together loosely by gravity that grows weaker the farther one travels from the core. At the very center sits a compact, extraordinarily dense core, no larger than a typical star like the Sun, where nuclear fusion still generates the energy that keeps the entire structure from collapsing. Surrounding that core is a vast, extended envelope of much cooler, much thinner gas stretched out across a radius so large that the term surface, in the ordinary sense, barely applies. Unlike the Sun, which has a sharply defined visible edge, Betelgeuse's outer layers thin out gradually into space, blending almost imperceptibly into an even more diffused shell of gas and dust the star has already ejected across thousands of years. For most of the 20th century, even the best telescopes could only infer this structure indirectly through brightness measurements and interferometry without ever producing an actual image. That changed in 1996 when astronomers Andrea Dupree and Ronald Gilliland used the Hubble Space Telescope's ultraviolet imaging capability to capture what was, at the time, the first direct image ever taken of the surface of a star other than the Sun. The resulting image showed a distinctly uneven, blotchy disk, with one region notably brighter than the rest, an early visual confirmation that Betelgeuse's surface was not smooth or uniform, but genuinely patchy, exactly as later more detailed observations would go on to confirm in far greater detail. If Betelgeuse were placed at the exact center of the solar system, its outer edge would extend past the orbit of Mars, and according to some recent estimates, possibly out toward the orbit of Jupiter itself. Earth, Mars, and the asteroid belt would all be swallowed inside a single star. This is not a metaphor or a simplification. It is a direct consequence of a measured radius currently estimated at somewhere between 750 and 1,000 times the radius of the Sun, a figure still refined periodically as new imaging technology becomes available. And yet, despite this almost incomprehensible size, Betelgeuse is not correspondingly massive in the way intuition might suggest. Current estimates place its mass at somewhere between 16 and 19 times the mass of the Sun, a large figure, but nowhere near 1,000 times larger, the way its volume alone might imply. The result of combining an enormous volume with a comparatively modest mass is a star with an average density far lower than that of ordinary air at sea level on Earth. In simple terms, Betelgeuse is less a solid, dense body and more an enormous tenuous cloud of gas, loosely held together, thinning out gradually rather than ending at any sharp, well-defined boundary. To place this in perspective, a cubic meter taken from deep within the Sun's core would weigh many times more than a cubic meter of solid lead, while a cubic meter taken from Betelgeuse's outer envelope would weigh barely more than the air inside an ordinary room on Earth. The star's mass, though genuinely enormous compared to the Sun, is spread across a volume so large that the material composing most of what would be called its body is closer to a thin glowing fog than to anything resembling a solid or liquid state. For decades, astronomers assumed that a star's surface, whatever its size, would behave in roughly the same way the Sun's does, covered in millions of small, roughly similar convection cells, rising columns of hot gas that carry energy up from the interior, cool slightly, and sink back down, a pattern visible on the Sun as a fine granulated texture. When astronomers finally obtained resolved images of Betelgeuse's surface, first through interferometry and later through direct imaging with instruments like the Atacama Large Millimeter Array, they found something different. Rather than millions of small convection cells, Betelgeuse's surface appears to be dominated by just a small handful of enormous convective structures, sometimes as few as 2 or 3, each one so large that a single cell can span a meaningful fraction of the star's entire visible surface. On the Sun, an individual convection cell, called a granule, typically measures around 1,000 kilometers across, roughly the width of a large country, and a single granule persists for only about 20 minutes before dissolving and reforming. A convective cell on Betelgeuse, by comparison, can measure hundreds of millions of kilometers across and persist not for minutes, but potentially for months or years at a time. These giant convection cells rise, cool, and sink far more slowly and unevenly than the Sun's, producing a surface that looks patchy and irregular when imaged, with some regions notably brighter and hotter than others at any given time. This structural difference is not fully understood, but current models suggest it arises directly from the star's low surface gravity combined with its enormous physical scale, a regime of stellar physics that behaves very differently from smaller, more compact stars like the Sun. This irregular, patchy surface behavior becomes especially important when trying to understand one of the most closely studied events in Betelgeuse's recent observational history: the sudden dramatic dimming that began in October 2019 and continued into early 2020, an event astronomers have since informally called the Great Dimming. Under normal conditions, Betelgeuse's brightness fluctuates within a fairly predictable range, governed by at least 2 overlapping rhythms. The shorter cycle, lasting roughly 400 days, is tied to genuine physical pulsations deep within the star, a rhythmic expansion and contraction of its outer layers, similar in principle to a slow, enormous heartbeat driven by pressure and temperature imbalances inside the envelope. A second, much longer cycle, stretching across nearly 6 years, puzzled astronomers for decades. For a long time, the leading guess was that it related to the position and behavior of the star's handful of giant convection cells, slowly shifting in and out of view, though a very different explanation for this same cycle, uncovered only recently, will emerge later in this story. Researchers analyzing over a century of brightness records, including a detailed 2018 study led by astronomer Laszlo Kiss, confirmed both of these overlapping periods and used them to help refine estimates of the star's internal structure, since the exact timing of stellar pulsations depends directly on a star's size, mass, and internal density profile. In October 2019, brightness measurements collected by this same long-running network of professional and amateur observers began showing a drop that exceeded anything in over a century of recorded data. By February 2020, the star had dimmed to roughly 40% of its typical brightness, a change large enough to be noticed by casual observers simply looking up at Orion without any instrument at all. For a star that has shone with essentially the same brightness for the entirety of recorded human history, a drop this size, this fast, immediately raised an uncomfortable question among astronomers. Was this the beginning of the end? News coverage at the time openly speculated about the possibility of an imminent supernova, and the story spread quickly, well beyond the astronomical community. Professional astronomers, while taking the event seriously as a genuine scientific mystery, generally urged caution, noting that a star's outer brightness can change dramatically for reasons entirely unrelated to core collapse. The task then was to determine which explanation actually fit the data, and that required new, targeted observations using some of the most capable instruments available. Two competing explanations emerged quickly, and for a period of months, neither could be fully ruled out. The first proposed that a large, unusually cool patch had developed on the star's surface, likely connected to the movement of one of its giant convection cells, temporarily reducing the amount of light reaching Earth from that region. The second, and ultimately more strongly supported explanation, proposed something more physically dramatic, that the star had ejected a massive plume of gas from its surface, which then cooled and condensed into a cloud of dust, drifting outward and partially blocking the star's light from Earth's point of view, much like smoke temporarily obscuring a lamp. In 2021, a research team led by astronomer Andrea Dupree, using ultraviolet observations from the Hubble Space Telescope alongside additional ground-based data, published findings supporting a combined explanation. According to this analysis, Betelgeuse likely experienced a genuine surface mass ejection, expelling a substantial quantity of material outward, equivalent to several times the mass of the Moon, which then cooled rapidly as it moved away from the star's hot surface, condensing into an opaque cloud of dust directly in the line of sight between Betelgeuse and Earth-based telescopes. This dust cloud, combined with a naturally cooler patch already forming on the surface due to the star's convection cycle, together accounted for the unprecedented drop in observed brightness. Additional evidence came from NASA's Transiting Exoplanet Survey Satellite, or TESS, a spacecraft originally designed to detect distant planets by measuring tiny dips in starlight, which happened to have Betelgeuse within its field of view during the dimming event. The extremely precise, continuous brightness data TESS collected allowed researchers to track the star's behavior in far finer detail than ground-based observation alone could provide, and this data strongly supported the combined dust and cool patch explanation, showing brightness fluctuations consistent with a physical structure passing across the star's disk, rather than any sudden internal change to the core. By April 2020, the star's brightness had already begun returning to its historical range, and by the following year, Betelgeuse had resumed its familiar, if irregular, cycle of dimming and brightening. The star had not exploded. It had, in effect, shed a portion of its own outer material into space, a behavior astronomers now understand to be part of a broader, ongoing process, rather than a singular, unprecedented event. Some researchers have since proposed a further layer to the explanation, suggesting that the same 400-day pulsation cycle that governs the star's ordinary brightness changes may have reached a peak at almost exactly the same moment as the dust ejection, amplifying the resulting dip in brightness far beyond what either event would have produced alone. Under this interpretation, the Great Dimming was not one unusual event, but two ordinary processes, a routine pulsation and a mass ejection, arriving at the same moment by coincidence and briefly combining into something that looked, from Earth, entirely unprecedented. That broader process is known as stellar mass loss, and in stars as large and unstable as Betelgeuse, it happens continuously, not only during dramatic events like the Great Dimming. Current estimates suggest Betelgeuse loses mass into surrounding space at a rate roughly 1 to 30 millionths of a solar mass per year. Because a single solar mass is roughly equal to 2 nonillion kilograms, even the smaller end of that range represents billions of tons of material leaving the star every single second, a rate thousands of times higher than the sun's own comparatively gentle solar wind. Over thousands of years, this steady outflow of gas and dust has built a faint, extended nebula surrounding the star, detectable in infrared observations, a shell of material the star has already shed during the final active stages of its life. Researchers studying this process have increasingly focused on a possible underlying cause, magnetic activity. A 2023 study using polarimetric observations, a technique that measures the orientation of light waves to detect magnetic fields, identified evidence of a surprisingly strong and organized magnetic field across portions of Betelgeuse's surface, stronger than models had previously predicted for a star of its type. Researchers now suspect that this magnetic field, combined with the enormous, slow-moving convection cells already documented, may work together to lift material off the star's surface and propel it outward into space, functioning as a kind of engine driving the continuous mass loss observed over the past century of monitoring. This remains an active area of research, with newer instruments specifically designed to map stellar magnetic fields in greater detail expected to refine this picture considerably in the coming years. Detailed imaging of the surrounding material, produced in 2017 by a research team led by astronomer Pierre Curvella using the Very Large Telescope in Chile, revealed structures resembling arcs, bow-shaped shells, and even bar-like features extending outward from the star across trillions of kilometers. One particularly large plume of material was found extending outward roughly 60 billion kilometers, more than 400 times the distance between Earth and the Sun, evidence of a substantial mass loss event that likely occurred long before the smaller Great Dimming episode of 2019. These structures are shaped in part by Betelgeuse's own motion through the surrounding interstellar medium, and in part by the uneven, patchy way the star ejects material from its irregular convective surface. Rather than losing mass in a smooth, symmetrical sphere, Betelgeuse appears to be shedding itself unevenly in plumes and clumps, a process that will continue with increasing intensity as the star moves closer to the true end of its life. Betelgeuse is not entirely alone in this behavior among visible stars. Antares, a red supergiant of similar size located in the constellation Scorpius, exhibits many of the same characteristics: an extended, patchy convective surface, irregular brightness variation, and a surrounding shell of previously ejected material. Its name, derived from ancient Greek, means roughly rival of Mars, a reference to its similarly reddish color and comparable brightness to the planet, a resemblance ancient skywatchers noticed independently of any understanding of what either object actually was. Because Antares and Betelgeuse are both nearing the ends of comparable lives, astronomers frequently study them side by side, using each star to help interpret unusual behavior observed in the other, a kind of comparative case study conducted across hundreds of light years of empty space. In 2017, the European Southern Observatory used the Very Large Telescope Interferometer to produce the first detailed map of gas motion across Antares' surface, tracing turbulent convective currents in a level of detail previously achieved only for Betelgeuse, confirming that the same giant, slow-moving convection cells documented on one star are very likely a general feature of red supergiants nearing collapse, rather than something unique to Betelgeuse alone. One additional detail has complicated the picture further. Careful measurements of Betelgeuse's rotation, published in recent years, suggest the star may be spinning significantly faster than current stellar models predict it should, given its size and the physical process by which stars typically expand into red supergiants, which normally causes rotation to slow dramatically as a star's radius grows, in much the same way an ice skater slows down by extending their arms outward. By ordinary physics, a star as bloated as Betelgeuse should be, rotating almost imperceptibly slowly, yet observations suggest its outer layers are turning at a rate far higher than expected. This unexpectedly rapid spin has led some researchers to propose an unusual hypothesis that Betelgeuse may have absorbed a smaller companion star at some point in its past, merging with it and inheriting its angular momentum, the rotational motion the smaller star once carried on its own. A 2024 analysis led by astrophysicist Jared Goldberg modeled this scenario directly and found that a merger occurring roughly 100,000 years ago could plausibly account for both the star's unusual spin and certain irregularities in its surrounding shell of ejected material. This remains an active hypothesis rather than a confirmed fact, one of several open questions that current and future observations, including higher resolution imaging planned with next-generation telescopes, may eventually help resolve. Betelgeuse was not always the bloated reddish star visible in Orion today. Based on its current mass and composition, astronomers estimate that it began its life as a hot blue-white star of roughly the same general type as Rigel, its neighbor across the constellation, burning hydrogen steadily at its core for a few million years, a strikingly short lifespan compared to the Sun's expected total lifetime of roughly 10 billion years. Massive stars burn through their fuel far faster than smaller ones, a direct consequence of the much higher core pressures and temperatures needed to support their far greater weight. And Betelgeuse's entire life, from formation to its current unstable state, has likely unfolded across only 8 to 10 million years, a blink of an eye compared to the Sun's much slower, steadier burn. At some point, estimated to have occurred roughly 1 million years ago, the hydrogen fuel in Betelgeuse's core was exhausted, triggering a dramatic restructuring. The outer layers of the star swelled outward hundreds of times over, its surface cooled and reddened, and the star transformed from a compact blue-white object into the enormous red supergiant now observed from Earth. This transformation is a normal, expected stage in the life of any sufficiently massive star, well understood and modeled extensively, though the exact timing and remaining duration of Betelgeuse's current stage, the final act before its core fully collapses, remains one of the central open questions driving continued observation. Everything visible on Betelgeuse's surface, the patchy brightness, the slow giant convection cells, the drifting plumes of ejected dust, is ultimately a symptom of something happening much deeper inside the star. Energy generated by nuclear fusion in the core does not reach the surface instantly. It is carried outward gradually, first through radiation near the core, and then across the vast majority of the star's interior, through convection itself, the same physical process visible on the surface as giant rising and falling cells of gas. In effect, the enormous, slow-moving patches astronomers observe from Earth are the outermost, visible tip of an energy transport system that begins at the core and stretches across hundreds of millions of kilometers to reach the point where light can finally escape into space. This connection matters because it means the surface of Betelgeuse is not an isolated feature, disconnected from what is happening at the center. It is a direct physical reflection of conditions inside the core, delayed and transformed by the long journey outward, but fundamentally linked to it. When the core's fusion process eventually changes, as it inevitably will, those changes will not stay hidden. They will, in time, be written across the very surface astronomers have spent more than a century learning to read. And inside that core, the changes have already begun. Taken together, the picture that emerges from decades of increasingly detailed observation is a star in visible turmoil, enormous beyond ordinary comparison, its surface dominated by a handful of slow, giant convective cells, its brightness fluctuating unpredictably, its outer layers actively peeling away into space, and possibly carrying the signature of a violent event in its past that current instruments can only partially detect. None of this instability is random. Every irregularity traces back to conditions building deep inside the star, in a core where the fundamental physics that has kept Betelgeuse shining for millions of years is now running out of fuel, one element at a time. Hydrogen fusion, the process that powered this star for the overwhelming majority of its life, ended long ago in its very center. What has been happening since, layer by layer, element by element, deeper and deeper inside the core, is the subject the next part of this story turns to directly. The final chain of nuclear reactions that will determine, ultimately, how and when the star's long life comes to an end. To understand what is happening inside Betelgeuse's core right now, it helps to understand what all stars do for most of their lives. A star spends the overwhelming majority of its existence fusing hydrogen into helium, a process that releases enormous energy and, more importantly, produces an outward pressure strong enough to counterbalance the star's own gravity, holding the entire structure in a stable, long-lasting equilibrium. This stage is called the main sequence, and for a star like the Sun, whose core burns at a comparatively gentle 15 million degrees Celsius, it lasts roughly 10 billion years. For a star as massive as Betelgeuse, gravity compresses the core far more intensely from the very beginning, driving core temperatures far higher than the Sun ever reaches, and forcing hydrogen to fuse at a dramatically faster rate. As a direct consequence, the main sequence for a star of this mass lasted only a few million years, and it ended roughly 1 million years ago, when the hydrogen fuel at the very center of the core was finally exhausted. What followed was not the end of fusion, but the beginning of a much faster, much more chaotic sequence of stages, each one burning a heavier element, each one requiring dramatically higher core temperatures, and each one lasting a fraction of the time of the stage before it. When core hydrogen runs out, gravity, no longer fully balanced by outward pressure, compresses the core further, raising its temperature until it crosses roughly 100 million degrees Celsius, hot enough to ignite a new fuel, helium, through a process called the triple alpha reaction. 3 helium nuclei fuse together to form a single carbon nucleus, releasing energy and once again temporarily restoring the balance between pressure and gravity. In a star of Betelgeuse's mass, helium fusion in the core is thought to last several 100,000 years, briefly stabilizing the star before the same pattern repeats. Once the core's helium supply is exhausted, gravity compresses it once more, driving the temperature past roughly 600 million degrees Celsius, and carbon begins to fuse, producing neon, sodium, and magnesium. This stage, carbon burning, proceeds far faster than the stages before it, lasting on the order of a few hundred to a few thousand years. A dramatic acceleration driven by the physics of nuclear fusion itself. Heavier elements require far higher temperatures to fuse, and at those temperatures, energy is both produced and lost far more rapidly than in cooler, earlier stages. A significant part of that accelerating energy loss comes from a subtle process called neutrino cooling. At the extreme temperatures reached during carbon burning and beyond, nuclear reactions inside the core begin producing large numbers of neutrinos directly, nearly massless particles that interact so weakly with ordinary matter that they escape the star almost instantly, carrying energy away with them as if the core had sprung a leak that no amount of pressure could seal. In the star's earlier hydrogen and helium burning stages, this effect is minor. In the final stages, it becomes the dominant force draining energy from the core, and it is the single biggest reason each successive fusion stage collapses in duration so dramatically. The pattern continues, each stage shorter than the last, and each one requiring higher core temperatures than the one before it. Neon burning, occurring above roughly 1.2 billion degrees Celsius, and converting neon into oxygen and magnesium, is estimated to last only around 1 year. Oxygen burning, igniting above 1.5 billion degrees Celsius, and producing silicon and sulfur, is thought to last mere months. By the time the core reaches its final fusion stage, silicon burning, ignited above approximately 2.7 billion degrees Celsius, the timescale has collapsed to somewhere between 1 day and 1 week. In this final stage, silicon nuclei fuse in a complex chain of reactions, ultimately producing iron and nickel at the very center of the star, elements that mark the true end of the fusion process, for reasons rooted directly in nuclear physics rather than any external event. This entire sequence produces a distinctive internal structure, one astronomers frequently compare to the layers of an onion, though the comparison, while visually useful, actually understates how differently each layer behaves. At the very center sits a small, extraordinarily dense core of iron and nickel, no larger across than a modest asteroid, no longer capable of producing energy through fusion. Surrounding that core, in successive shells, sit layers of silicon and sulfur, then oxygen, then carbon and neon, then helium, and finally, in the star's vast outer envelope, the hydrogen that has not yet been consumed at all. The proportions of this structure are strikingly lopsided. Current models suggest the iron core itself contains perhaps 1.5 to 2 solar masses of material, yet occupies a region only a few thousand kilometers across, comparable in size to Earth. The remaining bulk of the star, extending outward across hundreds of millions of kilometers, to reach the star's visible surface, consist overwhelmingly of the lighter, largely unprocessed hydrogen envelope, meaning that the vast majority of Betelgeuse's enormous physical size has almost nothing to do with where the star's actual nuclear activity and its impending crisis is taking place. Each of these shells continues to fuse its respective element, even as the core beneath it has already moved on to heavier reactions, meaning that at this stage in Betelgeuse's life, multiple fusion reactions are likely occurring simultaneously at different depths, each shell held in a delicate, temporary balance that will not last. This layered structure is not directly observable. No telescope can see inside a star. It is inferred entirely through theoretical models of stellar physics, built and refined over nearly a century and tested indirectly against the small number of observable clues a dying star does provide, including its surface temperature, its brightness, and the precise chemical elements detected in its outer atmosphere through spectroscopy. One of the few genuine windows into this hidden internal structure comes from spectroscopy of Betelgeuse's outer atmosphere, which has revealed measurable enrichment in nitrogen relative to carbon and oxygen, a chemical signature astronomers specifically expect from a process called dredge-up, in which convection reaching deep enough into the star's interior can carry processed material from regions near the core upward, mixing it into the visible outer layers. Detecting this exact pattern of enrichment in Betelgeuse's spectrum, rather than some other chemical signature, serves as indirect but meaningful confirmation that the layered fusion structure predicted by theoretical models is consistent with what the star's surface chemistry actually shows. Each fusion stage produces its own specific mixture of elements, a chemical fingerprint theoretical models track in careful detail. Carbon burning produces not only neon, but measurable quantities of sodium and magnesium, elements that will later be scattered into space and eventually incorporated into future generations of stars and planets. Neon burning proceeds through a subtler pathway in which high-energy photons first break neon nuclei apart before the fragments recombine into oxygen and magnesium, a process requiring temperatures so extreme that it only becomes possible in these final desperate stages of a massive star's life. It is worth pausing here on something easy to overlook in the sheer scale of these numbers. Every one of these elements, sodium, magnesium, silicon, all the way to the iron that will ultimately end this process, previously existed nowhere else in the universe in this exact form before being forged, one nuclear reaction at a time, inside a star exactly like this one. Because no instrument can observe a stellar core directly, astronomers rely heavily on computer simulations to model these final stages of a massive star's life, using software such as MESA, short for Modules for Experiments in Stellar Astrophysics, a widely used, continuously updated simulation code developed collaboratively by researchers around the world. Astrophysicist Stan Woosley, whose decades of work modeling the final stages of massive stars remains foundational to the field, has published detailed simulations tracing exactly this sequence of fusion stages, mapping how core temperature, density, and composition evolve second by second as a star approaches core collapse. These simulations cannot predict the exact day Betelgeuse's core will fail, but they provide the physical framework astronomers use to interpret every new observation of the star's surface as a possible signal of deeper change. The theoretical foundation for understanding this process was largely established in 1939, when physicist Hans Bethe published a landmark paper describing, for the first time, the specific nuclear reactions responsible for generating energy inside stars, work that would later earn him the Nobel Prize in Physics. Betelgeuse's early work focused primarily on hydrogen fusion, but it opened the door to a much broader field of research, understanding exactly which nuclear reactions occur inside stars, in what sequence, and at what rate, as a star ages and its core composition changes. That broader picture was completed in large part by a landmark 1957 paper, now commonly referred to by the initials of its four authors, Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle, often shortened to B²FH. This paper laid out, in comprehensive detail, the specific nuclear processes responsible for building every element heavier than hydrogen and helium found in the universe, including the precise sequence of fusion stages now understood to be occurring inside stars like Betelgeuse. Nearly every element on the periodic table heavier than helium, including the calcium in bone, the iron in blood, and the oxygen breathed by every living creature on Earth, was originally forged inside the core of a star very much like this one. Understanding why fusion stops at iron requires looking closely at a specific property of atomic nuclei called binding energy, essentially a measure of how tightly the particles inside a nucleus are held together, usually expressed in a unit called mega-electron-volts per nucleon. For elements lighter than iron, fusing two nuclei together releases energy because the resulting, larger nucleus is more tightly bound than the two smaller ones that formed it. This is the basic principle powering every fusion stage described so far, from hydrogen through silicon. If binding energy is plotted against the mass of each element, the resulting curve rises steeply for light elements, climbs more gradually through carbon, oxygen, and silicon, and reaches its highest point at iron and its close neighbor nickel, before beginning a slow decline through heavier elements like lead and uranium. This peak is not a coincidence of nuclear structure. It reflects a genuine balance between two competing forces inside the nucleus, the strong nuclear force pulling particles together, and the electric repulsion between positively charged protons pushing them apart, a balance that happens to be most favorable, most tightly bound, right around iron's 56 particles. Iron sits at that unique peak of the binding energy curve. It is the most tightly bound nucleus that exists in significant quantities inside stars, meaning it requires more energy to fuse iron into anything heavier than that reaction would release. In simpler terms, fusing iron does not produce energy. It consumes it, drawing energy away from the very process that has kept the star stable for its entire life. Once a star's core becomes predominantly iron, fusion can no longer generate the outward pressure needed to resist gravity, and the core, for the first time in the star's history, has no way left to hold itself up. A useful, if imperfect, comparison is a fire that has burned through every log within reach, and then, finding only stone left to burn, discovers that stone does not combust at all. It simply sits there, refusing to release the heat the fire needs to keep going. Iron functions, physically, in almost exactly this way inside a dying star's core. It is fuel that cannot be burned for energy, a dead end reached only after every lighter, usable element has already been consumed in sequence. Exactly where Betelgeuse currently sits within this sequence remains a genuinely unresolved question among astronomers, not simply an unknown detail, but an active scientific debate. A widely discussed 2020 study, led by astronomer Meredith Joyce, modeled the star's pulsation behavior and concluded that Betelgeuse is most likely still in the earlier stage of core helium burning, implying the star may have somewhere between roughly 100,000 years remaining before core collapse, a time frame that, while short astronomically, still stretches vastly beyond any human timescale. Other researchers, working from different assumptions about the star's mass and rotation, have argued for models placing Betelgeuse in a more advanced stage, though even these more urgent estimates do not suggest collapse is imminent within any single human lifetime with any confidence. This uncertainty exists precisely because the clues available from Earth, brightness, surface temperature, and pulsation timing, are indirect echoes of a process unfolding deep inside a structure no instrument can see through. Different research teams, feeding slightly different assumptions into their simulations, can arrive at meaningfully different conclusions about a core hidden behind hundreds of millions of kilometers of overlying stellar material. Resolving this uncertainty more precisely will likely require exactly the kind of long-term, continuous monitoring already underway, watching for the specific surface signatures that theoretical models predict should accompany each successive stage. In recent years, the James Webb Space Telescope has added a further layer of observational detail, capturing infrared images of the material surrounding Betelgeuse with a clarity earlier instruments could not achieve, tracing the star's surrounding dust structures back toward the surface ejection events responsible for creating them. While James Webb cannot see into the star's core any more than earlier telescopes could, its infrared sensitivity allows astronomers to study the cooler, outer material in far greater detail, refining estimates of how much mass the star has shed and how recently, data that feeds directly back into the same computer models used to estimate the star's current evolutionary stage. Were it possible to slice this star open and examine it directly, layer by layer, the picture would resemble nothing so much as a countdown already well underway, silent and entirely invisible from the outside, proceeding at a pace measured in years, then months, then days, accelerating steadily toward a conclusion the star's placid, ancient light gives almost no outward indication of. A hypothetical observer standing at a safe distance, somehow able to perceive the core's temperature directly, would watch each fusion stage ignite and burn out faster than the last, a flickering, accelerating countdown utterly disconnected from the calm, unchanging reddish light still reaching Earth 548 years later. From Earth, across that same vast distance of empty space, Betelgeuse still appears as it always has, a single, steady, reddish point of light in the shoulder of a hunter drawn across the winter sky by cultures that never knew what they were actually looking at. The physical principle limiting the iron core's size traces back to the pioneering work of physicist Subramanian Chandrasekhar, who in the 1930s calculated the precise mass limit beyond which electron degeneracy pressure can no longer support a stellar remnant against its own gravity, a boundary now known as the Chandrasekhar limit, set at approximately 1.4 times the mass of the Sun. Chandrasekhar's calculation initially met with significant resistance from some senior astronomers of his era, would later prove foundational not only to understanding the fate of smaller stars that end their lives as white dwarfs, but also to understanding precisely why massive stars like Betelgeuse cannot stop at this stage and must instead continue toward complete gravitational collapse. One additional consequence of this final countdown offers a genuine practical advantage to scientists on Earth, because the neutrinos produced during a star's final moments escape almost instantly, while visible light remains trapped inside the star's dense outer layers for hours longer. A global network of detectors called SNEWS, the Supernova Early Warning System, continuously monitors for a sudden simultaneous burst of neutrinos across multiple independent observatories worldwide. If Betelgeuse's core does collapse, this network is designed to detect the neutrino signal and alert astronomers hours before any visible change would appear in the sky, turning what might otherwise be a completely unpredictable event into one with at least a brief window of advance notice. Once the iron core reaches a critical mass, thought to be somewhere in the range of 1.4 to nearly 2 times the mass of the Sun, packed into a region roughly the size of Earth, the physics that has protected this star for millions of years fails entirely. Up until this point, the core has been supported not by fusion pressure alone, but by a quantum mechanical effect called electron degeneracy pressure, a resistance to compression that arises from a fundamental rule in physics preventing certain particles from occupying the same state. This pressure is remarkably strong enough to support a stellar core weighing more than the Sun, but it has a limit, and once the core's mass pushes past that limit, gravity, unopposed for the first time in the star's entire life, takes over completely. This same fate awaits every sufficiently massive star, including Antares, the red supergiant introduced earlier as Betelgeuse's closest observational counterpart, sitting in the constellation Scorpius and undergoing, deep in its own hidden core, a remarkably similar sequence of fusion stages on a broadly comparable timescale. Neither star's exact position within this sequence is known with certainty, and it remains entirely possible, though not established, that one or both have already reached their final moments, their light simply still making the centuries-long journey to Earth. It is worth noting that not every event popularly called a supernova follows this exact sequence. Some explosions, including several of the historical events this story will turn to shortly, are triggered by an entirely different mechanism, the runaway detonation of a compact stellar remnant called a white dwarf, typically after it pulls too much material from a companion star, rather than the iron core collapse of a still-living massive star like Betelgeuse. Both processes produce brilliant, sudden explosions bright enough to rival entire galaxies, but the underlying physics and the type of star involved are entirely different, a distinction astronomers carefully track by classifying each observed event according to the specific chemical signatures visible in its light. What distinguishes this particular stage of stellar evolution from everything the star has experienced before? It's not simply speed, though the acceleration from millions of years down to mere days is itself remarkable. It is the complete absence of any further option. Every previous crisis in the star's life, every exhausted fuel supply, was met with a new source of energy waiting one step further down the periodic table. Iron offers no such next step. It is the physical end of the road, the point at which the star's long negotiation with gravity, sustained since before recorded human history began, finally runs out of terms to offer. What happens next unfolds on a timescale almost impossible to reconcile with everything that came before it. A process that has taken millions of years to build, layer by layer, element by element, collapses in less than a single second, triggering one of the most energetic and violent events known to occur anywhere in the universe. The following part of this story picks up at precisely this moment, tracing the physical sequence of the collapse itself, second by fraction of a second, from the instant the core gives way to the shock wave that ultimately tears the star apart from the inside out. The collapse itself begins not with an explosion, but with a silence, a sudden and total withdrawal of the pressure that has held the core rigid for its entire existence, In the fraction of a second after the iron core exceeds its critical mass, the outward push that has resisted gravity for millions of years simply stops, and the innermost region of the star, roughly the mass of the Sun compressed into a sphere the size of Earth, begins falling inward under its own weight, accelerating toward the center at a significant fraction of the speed of light. This collapse is not gradual. Current models estimate that the inner core falls from a radius of a few thousand kilometers down to a radius of roughly 50 kilometers in well under a quarter of a second, a compression so extreme that it is difficult to find any everyday comparison that captures its scale. A structure that took millions of years to build now falls in on itself faster than a person could finish reading this sentence aloud. Two physical processes accelerate this collapse even further, feeding on each other in a runaway sequence. The first is called photodisintegration. At the extreme temperatures generated by the collapse itself, exceeding 10 billion degrees Celsius, high-energy photons begin striking iron nuclei directly, breaking them apart back into individual protons and neutrons, effectively unwinding in an instant the same nuclear fusion process that took the star millions of years to build layer by layer. This process absorbs enormous amounts of energy that would otherwise have helped resist the collapse, meaning that the very act of the core falling inward makes it fall inward faster still, a self-reinforcing feedback loop with no natural break until the core reaches nuclear density. The second process is called neutronization, or electron capture. As the core's density climbs to levels far beyond anything found anywhere else in the universe outside a collapsing star, free electrons are forced to merge directly with protons, converting them into neutrons and releasing a particle called an electron neutrino in the process, a reaction that would be forbidden under ordinary conditions, but becomes energetically favorable once the surrounding pressure grows extreme enough. This reaction, repeated an almost incomprehensible number of times throughout the collapsing core, strips away much of the electron pressure that had been helping support the core's structure, further accelerating the collapse while simultaneously producing the first wave of a phenomenon that will soon dominate the entire event. That phenomenon is the neutrino burst, and its scale is genuinely difficult to convey in ordinary terms. Within the first fraction of a second of core collapse, the star produces and releases something on the order of 10 to the 58th power neutrinos, a number so large it exceeds the total count of atoms in the observable bodies of every human being who has ever lived, combined many times over. These neutrinos carry away roughly 99% of the total energy released by the entire collapse and subsequent explosion, an amount of energy comparable to the Sun's total output across its entire 10 billion year lifetime, released in a matter of seconds. Because neutrinos interact so weakly with ordinary matter, this staggering burst of energy passes directly through the remaining bulk of the collapsing star as though it were barely there at all, escaping into space almost instantly, while the visible light from the explosion itself remains trapped inside the star's outer layers for hours, sometimes longer, before it can finally break free. This theoretical picture of a neutrino burst preceding visible light was not simply an assumption. It was directly confirmed by observation in February 1987, when a supernova occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way located roughly 168,000 light-years from Earth. 3 separate neutrino detectors, built for entirely unrelated physics experiments and located in Japan, the United States, and Russia, each independently recorded a brief burst of neutrinos arriving within seconds of one another, approximately 2 to 3 hours before the supernova's visible light was first observed by astronomers. This event, catalogued as SN 1987A, remains the only supernova in modern astronomical history from which neutrinos have been directly detected, and it provided direct experimental confirmation of a physical process that, until that moment, existed only inside theoretical models and computer simulations. The collapse does not continue indefinitely. Once the core's density reaches a level comparable to the density of an atomic nucleus itself, roughly 400 trillion times denser than water, a new force takes over. The strong nuclear force, the same force that binds protons and neutrons together inside every atom, suddenly resists further compression with tremendous strength. The collapsing material, falling inward at a significant fraction of the speed of light, slams into this newly rigid core and rebounds, a physical event astronomers refer to as the core bounce. The core bounce is in a sense the star's material, discovering that it has run out of room to compress any further, a wall made not of solid matter in the ordinary sense, but of a fundamental quantum resistance between neutrons, packed as tightly as the laws of physics permit. The rebound is nearly instantaneous, and the outward moving material briefly overshoots its new equilibrium before settling, generating pressure waves that ripple outward through the surrounding, still collapsing layers above it, forming the initial shock wave. If the collapse proceeds asymmetrically, as current simulations suggest is likely given the turbulent, uneven convection already observed on Betelgeuse's surface, the violent motion of matter during collapse and bounce should also generate gravitational waves, ripples in the fabric of space-time itself, similar in nature to those first directly detected from colliding black holes in 2015. At Betelgeuse's distance of roughly 548 light-years, a genuine core collapse event would likely produce a gravitational wave signal strong enough for detectors such as LIGO and Virgo to register clearly, offering scientists a third independent channel of data, alongside neutrinos and light, through which to observe the star's final moments in close to real time. This bounce sends a powerful shock wave racing back outward through the still infalling material above it, and for decades, the central unsolved problem in supernova physics was understanding what happens to that shock wave next. Early computer models consistently found that the rebounding shock wave, as it travels back outward, loses energy rapidly to exactly the same photodisintegration process that accelerated the initial collapse, breaking apart the iron and silicon nuclei still falling inward from higher layers of the star, and stalling before it can escape the core entirely, typically within a few hundred kilometers of where it began. A stalled shockwave, left alone, would not produce an explosion at all. It would simply fail, and the entire outer envelope of the star would fall back inward onto the newly formed core, an outcome computer models struggled with for years, since it directly contradicted the fact that massive stars are observed to explode. This was not a minor technical difficulty. For several decades beginning in the 1960s, one-dimensional computer models, the only kind early computing power could support, consistently produced failed explosions, or none at all, an embarrassing and persistent gap between theory and observation that troubled the field for a generation of researchers. The resolution to this problem developed primarily through the work of physicists Hans Bethe and James Wilson in the mid-1980s, and refined extensively since through increasingly sophisticated supercomputer simulations, centers on the neutrinos themselves. It was not until computing power advanced enough to support genuine three-dimensional simulations incorporating the full complexity of turbulent convection behind the shockwave, that models finally began reproducing successful, self-sustaining explosions consistently, a milestone reached only within roughly the past 15 years. Although the vast majority of neutrinos produced during collapse escape the star entirely without interacting with anything, the sheer number produced means that even the small fraction that do interact with the stalled shockwave region, roughly 1 in every 100,000, deposit enough energy to reheat and reinvigorate it. This delayed neutrino heating mechanism, combined with large-scale, turbulent convective motion behind the shock that current simulations show developing within the first second after bounce, together appear capable of reviving the stalled shockwave and driving it back outward with enough force to finally escape the core and tear through the remaining layers of the star above it. Modern three-dimensional supercomputer simulations, including extensive work led by astrophysicist Adam Burrows and collaborators, have finally succeeded in modeling this entire sequence self-consistently, from initial collapse through neutrino-driven shock revival to a genuine, successful explosion, a computational achievement that took the field several decades of steadily increasing computing power to accomplish. These simulations remain enormously demanding even on the most powerful supercomputers currently available, often requiring millions of processor hours to model just a few seconds of physical time inside a single dying star, run on some of the same research computing clusters used to model climate systems and nuclear reactor physics. The unusually rapid rotation documented on Betelgeuse's surface, discussed earlier in this story alongside the hypothesis that it may have absorbed a smaller companion star, carries direct consequences for how its eventual collapse would unfold. Current models suggest that a more rapidly rotating core collapses less symmetrically than a slowly rotating one, potentially channeling more explosive energy outward along the star's rotational poles than along its equator, producing an explosion with a distinctly lopsided geometry rather than a perfectly even sphere. In the most extreme cases of rapid rotation, this asymmetry can grow strong enough to produce a narrow, highly energetic jet capable of generating a gamma-ray burst, though current mass and rotation estimates for Betelgeuse fall well short of the extreme values typically associated with that particular, rarer outcome. Once revived, the shockwave proceeds outward through the remaining layers of silicon, oxygen, carbon, helium, and finally hydrogen, compressing and heating each layer as it passes, triggering brief explosive nuclear reactions in material that would otherwise never have fused at all, a process called explosive nucleosynthesis. This final violent burst of fusion, lasting only seconds as the shockwave passes through, is responsible for producing many of the elements heavier than iron found scattered throughout the universe, elements that cannot form through ordinary stellar fusion because, as established earlier, fusing elements heavier than iron consumes energy rather than releasing it, and can only occur when an external source, in this case the shockwave itself, forces the reaction regardless of the energy cost. Some of the heaviest elements in the universe, including gold, platinum, and uranium, form through a related but distinct process called rapid neutron capture, in which atomic nuclei absorb neutrons in extremely dense, neutron-rich environments faster than the resulting unstable nuclei have time to decay. For decades, core collapse supernovae like the one Betelgeuse will eventually undergo were considered the leading candidate site for this process, though observations over the past decade, particularly following the detection of a neutron star merger in 2017, accompanied by both gravitational waves and direct spectroscopic evidence of freshly synthesized heavy elements, have led researchers to conclude that neutron star collisions likely produce the majority of the universe's heaviest elements, with supernovae contributing a smaller, though still meaningful, share. The shock wave eventually reaches the star's outer surface, hundreds of millions of kilometers from where the collapse began, in a journey lasting several hours after the initial core bounce, since even a shock wave moving at a meaningful fraction of the speed of light still requires real time to cross a distance that large. When it finally breaks through, it produces an intense flash of high-energy radiation known as shock breakout, followed within minutes by a dramatic brightening of the star's visible light as the explosion's energy is released into space. Over the following days and weeks, the exploding star's brightness would climb further still, eventually making it, for a period of weeks, one of the brightest single objects in the night sky, rivaling the full moon in total brightness and remaining visible even during daylight hours. For any observer on Earth's night side at the moment of peak brightness, the shoulder of Orion would no longer hold a modest reddish point of light, but something closer to a small, fierce lamp, casting faint shadows on a clear, dark night the way a crescent moon might, an anomaly bright enough to draw notice from anyone who happened to glance upward, whether or not they understood astronomy at all. Within a few months, that brilliance would begin a slow, steady fade, over years eventually settling into the faint glow of an expanding, cooling remnant, the visible portion of the story concluding roughly the way it began, quietly and easily missed by anyone not specifically watching for it. For a star located 548 light-years away, this brightness, while extraordinary as a sky event, poses no meaningful danger to Earth. The most severe potential hazard from a nearby supernova comes from an initial pulse of high-energy gamma radiation and cosmic rays capable of stripping away a meaningful fraction of a planet's protective ozone layer and increasing surface radiation exposure. But scientific estimates place this danger zone at only around 25 to 50 light-years, a distance more than 10 times closer than Betelgeuse actually sits. At its current distance, Betelgeuse's eventual explosion would be an extraordinary, harmless spectacle, bright enough to cast shadows at night for a period of weeks, but posing no measurable threat to Earth's atmosphere, climate, or biosphere. This raises the genuinely strange possibility hinted at earlier in this story. Because light from Betelgeuse takes 548 years to reach Earth, it remains entirely possible, though considered unlikely by most current models, that this exact sequence of collapse and explosion has already occurred sometime in the centuries since the light currently visible in the night sky first departed the star's surface. The year 548 years ago corresponds to 1478, decades before Columbus's voyages, during the final years of the Byzantine Empire's slow decline, a period from which the light now reaching Earth's telescopes actually departed. If the collapse has already happened, the news simply has not arrived yet, still crossing the intervening distance at the fixed, unchangeable speed of light, carrying with it an event that, from the star's own perspective, is already ancient history. Every photon of that ordinary, steady red light still reaching Earth tonight is, in a strict physical sense, outdated information, an image of a star that may no longer exist in the form it appears to, delayed by the unavoidable limits of how fast information can travel through the universe. What remains behind once the explosion's visible light finally fades from Earth's sky over the following months depends on precisely how much material falls back onto the collapsed core during and after the explosion. In many cases, the collapsed inner core survives as an incredibly dense object called a neutron star, typically no larger than a city, roughly 20 kilometers across, yet containing more mass than the Sun, packed together at nuclear density, a single teaspoon of its material weighing, in principle, as much as a mountain on Earth. Many neutron stars, formed with the leftover rotational motion of their parent star's core, spin extremely rapidly, some completing hundreds of rotations every second, and emit narrow, focused beams of radiation from their magnetic poles that sweep across space like a lighthouse as the star rotates. If one of these beams happens to sweep across Earth's line of sight, the object is detectable as a pulsar, a precisely timed cosmic clock so regular that early radio astronomers briefly wondered whether the first ones detected, in 1967, might be artificial signals. Some neutron stars additionally develop extraordinarily powerful magnetic fields, trillions of times stronger than Earth's own, earning the separate designation magnetar, objects capable of occasional starquakes violent enough to be detected from other galaxies. In other cases, particularly for the most massive progenitor stars, enough material falls back onto the core that its mass exceeds a second critical threshold, and it continues collapsing further still, forming a black hole instead, an object dense enough that not even light can escape its gravity. Current estimates place Betelgeuse's mass close to the boundary between these two possible outcomes, meaning astronomers cannot yet say with confidence which remnant its eventual collapse will leave behind, a genuine open question that will only be resolved when and if the event is finally observed. Whichever outcome occurs, the vast majority of the star's outer material, the hydrogen envelope, the layers of processed elements built up across its final million years, will be blasted outward into the surrounding galaxy at velocities reaching several percent of the speed of light, forming an expanding remnant that will continue glowing for thousands of years. This expanding debris field, called a supernova remnant, will gradually cool, slow, and mix into the surrounding interstellar medium over tens of thousands of years, spreading the newly forged elements, carbon, oxygen, silicon, iron, and everything created in the final explosive burst of fusion across a volume of space many light years wide. The remnant's expanding shockwave also accelerates charged particles to extraordinary energies as it plows through surrounding gas, a process astronomers believe is responsible for producing a significant share of the cosmic rays that constantly rain down on Earth's atmosphere, high-energy particles whose ultimate origin, in many cases, traces back to a supernova shockwave from thousands or millions of years earlier. Some fraction of that material will eventually be swept up into future molecular clouds, the same kind of star-forming nurseries responsible for Betelgeuse's own birth roughly 10 million years ago, continuing a cycle of stellar birth, death, and rebirth that has been running continuously across the galaxy for more than 10 billion years. The uncertainty over exactly when this entire sequence will occur sits in the background of every unusual observation astronomers make of Betelgeuse, including the Great Dimming event of 2019 and 2020 described earlier in this story. At the time, alongside the competing dust cloud and cool patch explanations, researchers also checked, as a matter of routine caution, whether the Supernova Early Warning System network had detected any unusual neutrino activity coinciding with the dimming. It had not, a null result that, while not glamorous, provided meaningful reassurance. Whatever was happening on Betelgeuse's visible surface in early 2020, it was not accompanied by the telltale neutrino signature of a collapsing core, effectively ruling out core collapse as an explanation for that particular event, well before the dust cloud explanation was fully confirmed. Events like this are not merely theoretical. Human observers have witnessed several supernovae with the naked eye throughout recorded history, bright new stars appearing suddenly where nothing had been seen before, carefully documented centuries before anyone understood what these sudden lights actually represented. In each of those historical cases, a star underwent precisely the sequence described here: collapse, bounce, neutrino burst, shock wave revival, and explosive breakout, invisible and unknown to the observers on Earth, who simply looked up one night and found a new light where none had been before. The next part of this story turns to those historical accounts directly, tracing what ancient astronomers across multiple civilizations actually recorded when they looked up, and without knowing it, witnessed the deaths of stars, very much like the one still burning quietly in the shoulder of Orion tonight. Nearly 9 centuries before the guest star of 1054 appeared, Chinese astronomers had already documented an even earlier event of this kind. In December of the year 185, observers during the later Han Dynasty recorded a bright new star appearing near the constellation, now known as Centaurus, describing it in official records as gradually fading over roughly 8 months, sometimes brightening and dimming irregularly during that period. Modern astronomers, tracing the expansion of a faint, wide, roughly circular remnant, now catalogued as RCW86, have connected this ancient description to what most researchers now consider the oldest reasonably well-documented supernova observation in recorded human history. On the morning of July 4th, in the year 1054, astronomers at the imperial court of Song Dynasty China recorded something extraordinary in the sky near the constellation Taurus, a new star bright enough to be seen in broad daylight for the following 23 days and visible at night for nearly 2 years afterward. Official court records, later compiled into the History of Song, described it as a guest star, a term used across centuries of Chinese astronomical record-keeping for any bright new light appearing where none had been charted before. Chinese court astronomers had recorded similar guest stars for centuries before 1054, part of a long, largely unbroken tradition of careful sky observation maintained for calendrical and astrological purposes by successive dynasties. This tradition would later prove enormously valuable to 20th century astronomers who lacked any other reliable way to date ancient supernova precisely. By carefully measuring the current expansion rate of the resulting nebula and calculating backward to determine when its material must have begun expanding from a single point, researchers in the 1920s arrived at a date strikingly close to 1054, and the surviving Chinese court records provided the confirming historical anchor that transformed an approximate calculation into a confirmed, dated event. This guest star of 1054 was not unique to Chinese observation. A separate account, attributed to an Arab physician named Ibn Butlan, writing from Constantinople, appears to describe a comparable bright new light in the sky around the same period, though the exact details and dating in surviving Arabic sources remain debated among historians. Some archaeologists have additionally proposed that a rock art panel found at Chaco Canyon in present-day New Mexico, depicting a crescent moon alongside a bright starburst shape, may represent an ancestral Puebloan record of this same event, since the moon's position on the night of July 5th, 1054, would have placed it in close conjunction with the new star, though this interpretation remains debated rather than confirmed among researchers. Skeptics note that similar crescent and star petroglyphs appear at other sites without any connection to known astronomical events, and that pinning a specific carving to a specific date, made without any written record explaining its intent, is inherently difficult to verify with confidence. The debate remains active, a reminder that even physical, carved evidence does not always settle a historical question as cleanly as a written record might. What none of these observers could have known is that they were watching the death of a massive star, its core collapsing and rebounding in precisely the sequence described earlier in this story. Its outer layers blasted outward in an explosion so bright it briefly outshone every other star in the sky. Today, the expanding debris from that explosion is known as the Crab Nebula, a glowing filamentary cloud of gas spanning roughly 11 light-years, still expanding outward at over 1,500 kilometers per second, nearly 1,000 years later. The Crab Nebula holds a particular significance in the history of astronomy itself. In 1758, while searching the sky for a comet, French astronomer Charles Messier came across this same faint, fuzzy patch of light, and realizing it could easily be mistaken for a comet by future observers, began compiling a catalog of similar objects specifically to help astronomers avoid that exact confusion. That catalog, eventually containing over 100 entries, remains in active use today, and the Crab Nebula, as Messier's first entry, is still commonly referred to by the designation M1. At the Crab Nebula's core sits the collapsed remnant of the original star, a neutron star spinning approximately 30 times every second, sweeping a beam of radiation across space with each rotation, detected on Earth as one of the most precisely timed pulsars known to astronomy. Its discovery in 1968 provided some of the first direct observational evidence connecting historical guest star sightings to the specific physical remnants predicted by theoretical models of stellar collapse, closing a loop between ancient observation and modern astrophysics that had taken nearly a millennium to complete. More than 5 centuries later, on November 11, 1572, a Danish astronomer named Tycho Brahe stepped outside after dinner and noticed a bright, unfamiliar star in the constellation Cassiopeia, one that, by his careful measurements, showed no detectable daily shift in position relative to the surrounding stars, exactly as a genuinely distant star would behave, and entirely unlike a comet or planetary phenomenon closer to Earth. At its peak, the new star rivaled the brightness of Venus and remained visible even during daylight hours, gradually fading from view over the following 16 months. Working decades before the invention of the telescope, Tycho relied entirely on large, precisely engineered naked-eye instruments, quadrants and sextants built at a scale and craftsmanship far exceeding anything available to earlier European astronomers. His resulting star catalog would prove accurate enough that it remained the most reliable in Europe for decades, and the same meticulous observational standard he applied to ordinary stars, he applied equally to this new and unexpected one. The Danish king, impressed by Tycho's growing reputation, later granted him the island of Hen, where Tycho built an entire dedicated observatory complex named Uraniborg, specifically to continue this kind of precise, systematic sky monitoring. Tycho's careful, methodical observations of this event, published shortly afterward, carried consequences that extended far beyond astronomy alone. For nearly 2,000 years, European scholarship had operated under the Aristotelian assumption that the heavens beyond the moon were perfect, unchanging, and eternal, incapable of producing anything genuinely new. A bright new star, appearing suddenly among the supposedly fixed and eternal backdrop of distant stars, directly contradicted that assumption, and Tycho's meticulous measurements, demonstrating the object's genuine distance, made the contradiction difficult to dismiss. This event, still referred to today as Tycho's supernova, played a meaningful role in the broader intellectual shift then underway across Europe, one that would, within decades, help pave the way toward the wider acceptance of a fundamentally different picture of the universe, one where the heavens were not fixed and unchanging after all. Modern observations of the resulting remnant, using X-ray telescopes such as NASA's Chandra Observatory, have confirmed that Tycho's star was a specific category of stellar explosion, distinct from the core collapse process described earlier in this story, one triggered instead by the runaway detonation of a dense stellar remnant called a white dwarf. Just over 3 decades after Tycho's observation, on October 9, 1604, another bright new star appeared, this time in the constellation Ophiuchus, and was tracked in extensive detail by the German astronomer Johannes Kepler, whose name it still carries today. At its peak brightness, Kepler's star outshone every planet and every star in the night sky except Venus, remaining visible to the naked eye for roughly a year before gradually fading from view. Kepler published a detailed account of his observations, tracking the star's changing brightness and color night after night with the same rigorous precision he was around this same period, applying to his groundbreaking work on the orbits of the planets. The timing carried an additional layer of significance for observers at the time. The new star appeared just as Jupiter and Saturn were passing unusually close together in the sky, a rare planetary conjunction many contemporary observers regarded as astrologically significant in its own right, making the sudden appearance of a brilliant new star in the same region of sky feel, to much of the public, like an unmistakable omen. Kepler himself, while personally holding some astrological beliefs typical of his era, approached the star's actual physical nature with careful scientific rigor, correctly identifying it as a genuinely new, distant object rather than any kind of atmospheric or astrological phenomenon. The astronomer Galileo Galilei, observing independently from Italy, used this same event in public lectures to further challenge the lingering Aristotelian belief in an unchanging cosmos, adding his own observational authority to the argument Tycho had begun 3 decades earlier. Kepler's supernova of 1604 holds one further distinction. In the more than 4 centuries since it was observed, no other supernova has been confirmed by naked eye observation from within the Milky Way galaxy itself, an unusually long gap given how many massive stars our galaxy contains, and one astronomers attribute largely to interstellar dust, which can obscure a distant explosion's visible light almost entirely, even when the underlying physical event was every bit as violent as the ones witnessed in 1054, 1572, and 1604. That obscuring effect may explain a curious historical footnote from 1680, when the English astronomer Royal John Flamsteed catalogued a faint star in the constellation Cassiopeia, listing its position carefully among thousands of others in his survey of the night sky. No star has ever been found at that exact recorded position since. Some astronomers now suspect that Flamsteed may have unknowingly observed a supernova, one whose visible light was heavily dimmed by intervening dust, faint enough to be logged as an unremarkable star rather than recognized as anything unusual, its true nature only becoming clear centuries later through the discovery of an expanding remnant, now called Cassiopeia A, at precisely that location in the sky. When NASA's Chandra X Ray Observatory captured its very first calibration image in 1999, mere weeks after launch. It happened to point toward Cassiopeia A, and the resulting image revealed something remarkable. A bright, compact point source, sitting almost exactly at the remnant's center, the collapsed neutron star left behind by whichever massive star exploded there roughly 3 centuries earlier. More recent observations using the James Webb Space Telescope have resolved the remnant's tangled filaments of expelled gas in extraordinary detail, mapping the precise chemical composition of debris that includes many of the same elements: silicon, sulfur, oxygen, and iron, whose formation was traced step by step earlier in this story. The most recent supernova to be studied in detail occurred not in our own galaxy, but in a nearby one. On February 23, 1987, a Canadian astronomer named Ian Shelton, working at Las Campanas Observatory in Chile, noticed a new point of light on a photographic plate of the Large Magellanic Cloud, a small satellite galaxy of the Milky Way located roughly 168,000 light-years from Earth. Unlike the 1054, 1572, and 1604 events, this explosion, designated SN 1987A, could be matched directly to a specific star already cataloged in earlier surveys of that region, a blue supergiant known as Sandelike 69202. This identification came as a genuine surprise to the astronomical community, since existing theoretical models at the time predicted that core collapse supernovae should originate almost exclusively from red supergiants, stars like Betelgeuse, rather than hotter, more compact blue supergiants. SN 1987A forced astronomers to revise those models, incorporating the possibility that some massive stars might shrink and heat up again shortly before their final collapse, depending on their exact mass, rotation, and chemical composition, a reminder that even well-established theoretical frameworks require continual revision as new observational evidence arrives. As described earlier in this story, this same event provided the first and to date only direct detection of neutrinos from a supernova's core collapse, recorded by 3 independent detectors hours before the explosion's visible light reached Earth, transforming a purely theoretical prediction into confirmed observational fact. Because SN 1987A occurred close enough for detailed, sustained study and far enough away to pose no conceivable danger, it has served for nearly 40 years as the single most valuable natural laboratory astronomers have ever had for testing supernova theory against direct, repeated observation. In the years following the explosion, the Hubble Space Telescope captured a striking and unexpected structure surrounding SN 1987A, 3 separate, glowing rings of gas arranged in a complex layered pattern unlike anything predicted by simple explosion models. The prevailing explanation suggests these rings were shaped by material ejected from the star long before its final collapse, sculpted into this unusual geometry by interactions with a close companion star whose gravity is thought to have carved the surrounding gas into rings well before the explosion ever occurred. Beginning in the late 1990s, astronomers watched as the supernova's own expanding shock wave gradually caught up to and began colliding with the inner of these 3 rings, producing a spectacular sequence of bright hotspots that appeared one after another around the ring's circumference, in effect some researchers nicknamed a string of pearls. This ongoing collision, still being tracked by telescopes today, offers a slow-motion, real-time demonstration of precisely the kind of shockwave material interaction that on a much larger and far more violent scale will one day determine how Betelgeuse's own surrounding shells of previously ejected dust and gas respond when its shockwave finally reaches them. Nearly 40 years after the original explosion, the question of exactly what collapsed core, if any, survived at the center of SN 1987A remained unresolved, since thick surrounding dust made it impossible to see directly for decades. In 2024, using the James Webb Space Telescope's infrared instruments, researchers detected a specific chemical signature, ionized argon and sulfur, in a pattern consistent with intense radiation from a compact object embedded in the remnant's center, providing the strongest evidence yet that a neutron star did indeed form and survive the explosion, hidden from direct view but no longer entirely invisible to sufficiently advanced instruments. That detail carries a particular resonance for the star at the center of this story. For much of the 20th century, astronomers suspected that Betelgeuse itself might have a hidden companion star based on subtle, long-period variations in its brightness that a red supergiant's pulsations and convection alone could not fully explain. Early searches using conventional imaging repeatedly failed to find any such companion, largely because Betelgeuse's own overwhelming brightness made it nearly impossible to detect a much fainter object situated so close beside it, a persistent observational challenge that spanned decades of failed attempts. That suspicion was finally confirmed in July 2025, when a research team led by astronomer Steve Howell, using specialized high-resolution imaging on the Gemini North Telescope in Hawaii, successfully captured a faint point of light beside Betelgeuse, appearing exactly where more than a century of indirect evidence had predicted it should be. The team had imaged the same region in 2020, during a period when models predicted the companion would be hidden directly behind Betelgeuse from Earth's perspective, and found nothing precisely as expected. A second attempt in December 2024, timed for the companion's predicted point of widest separation, finally revealed a faint object exactly 52 milliarseconds from Betelgeuse, in exactly the position and brightness multiple independent models had forecast. The newly confirmed companion, estimated at roughly 1.6 times the mass of the Sun and orbiting once every 6 years, was later given the name Siwarha, Arabic for her bracelet, a fitting counterpart to Betelgeuse's own name, believed to mean the hand or shoulder of the great figure it sits within. Researchers now believe Siwarha is a young, still-forming star, one that orbits so closely it actually passes directly through Betelgeuse's enormous extended outer atmosphere during each circuit, an almost unimaginably turbulent environment for a smaller star to repeatedly traverse. This close, ongoing interaction also offers a simpler possible explanation for Betelgeuse's unexpectedly rapid rotation, discussed earlier in this story. Rather than requiring a past merger with a since-absorbed star, a smaller companion physically dragging through the giant's outer layers on every orbit could, over time, transfer enough angular momentum through tidal interaction alone, meaning the two competing explanations, merger and companion, may not be mutually exclusive, and further research will be needed to determine how much each has actually contributed. Further confirmation followed within months. In January 2026, astronomer Andrea Dupre, the same researcher whose earlier work helped explain the Great Dimming event of 2019, announced additional evidence gathered using the Hubble Space Telescope, a faint, dense trail of gas extending through Betelgeuse's outer atmosphere, consistent with a companion star physically plowing through the giant's extended envelope as it orbits. This wake of disturbed material offers a direct physical explanation for irregularities in Betelgeuse's brightness that had puzzled astronomers for well over a century, a mystery finally approaching resolution almost exactly 100 years after Pease and Michelson's first measurement of the star's enormous size. Whether Sawara will survive long enough to witness Betelgeuse's eventual collapse, or whether its presence will meaningfully shape the geometry of that explosion the way a suspected companion appears to have shaped the rings surrounding SN 1987A, remains an open question, one current researchers are actively working to answer through continued observation. What is certain is that the study of Betelgeuse, much like the study of every supernova recorded across the centuries before it, continues to reveal new layers of complexity with each generation of instruments capable of looking more closely. 4 historical events, spanning more than 9 centuries and multiple civilizations, each began the same way: an ordinary night, a familiar sky, and then, without warning, a light where no light had been before. Song Dynasty court astronomers, a Danish nobleman, a German mathematician, and a Canadian observer working alone at a mountain observatory each, in their own time, looked up and witnessed the same fundamental physical event now understood in careful detail throughout this story. None of them knew in the moment exactly what they were seeing. They only knew that something had changed. A star that had always been there, or had not been there at all, now hung differently in the sky. Word spread, records were kept, sometimes for reasons of astrology, sometimes simply out of careful habit, and those records outlived the observers who made them by many centuries. It is only now, with instruments those observers could never have imagined, that their careful notes can finally be matched against the true physical cause behind each sudden light, the quiet collapse of an aging star's core, the sequence traced in careful detail throughout this story, repeating itself across the galaxy on a timescale far slower than any single human life, yet often enough that a handful of these events have found their way into written human history at all. Somewhere above Orion tonight, that same slow process continues, unseen, unheard, patiently working its way through the final stages of a star that has already outlived the empires and observatories of everyone who first gave it a name. That same slow process continues tonight above Orion, unseen and unheard, patiently working its way through the final stages of a star that has already outlived the empires and observatories of everyone who first gave it a name. Whenever that process finally reaches its conclusion, whether centuries from now or in the strange physics of light delay, already finished and simply not yet visible, the star's material will not disappear. It will scatter outward across the galaxy, carrying with it the same elements traced carefully throughout this story: the carbon, the oxygen, the silicon, the iron, each one forged inside a stellar furnace across a lifetime measured in millions of years. Somewhere, eventually, some fraction of that scattered material will drift into a cold, quiet molecular cloud, the same kind of stellar nursery that gave rise to Betelgeuse itself roughly 10 million years ago. There, gravity will slowly gather it together again, compressing gas and dust into new stars, new planets, and, given enough time and the right conditions, potentially into the basic chemical building blocks of life itself. This process is neither rare nor especially dramatic from the universe's perspective. It has already happened an uncountable number of times across the history of the Milky Way, each dying massive star quietly seeding the next generation of stellar nurseries with slightly more of the heavier elements than existed before, a slow chemical enrichment stretching back to the earliest stars the universe ever produced, which contained almost nothing but hydrogen and helium at all. This is not a metaphor. It is simply how the universe manufactures the heavier elements found in every planet, every ocean, and every living creature currently known to exist. Every star that has ever died in exactly this way has contributed to that same slow, patient accumulation, one generation of stellar material recycled into the next, stretching back across cosmic time to the very first stars that ever formed. The Sun itself is a direct product of this same process. Chemical analysis of the solar system, from meteorites to the composition of the Sun's own outer layers, shows measurable quantities of elements that can only have been produced inside earlier generations of stars and scattered into the cloud of gas from which the Sun and its planets eventually formed roughly 4.5 billion years ago. Every heavy element in Earth's core, every trace of iron in its crust, every atom of calcium, phosphorus, and oxygen found in living things anywhere on this planet traces back through this same chain, generation after generation of stars living, dying, and scattering their contents outward. Betelgeuse's own story began the same way, gathered from the scattered remains of stars that lived and died long before it in an earlier era of the galaxy's history. And when its own turn finally comes, its material will simply continue that same unbroken chain, joining the slow, ongoing work already carried out by every star that came before it. Tonight, across observatories and backyards scattered around the world, that same quiet star still holds its place in Orion's shoulder, exactly where it has always been. Professional astronomers working through observatories in Chile, Hawaii, and dozens of other sites around the globe continue collecting data on its brightness, its surface, and its subtle, ongoing changes. Amateur observers, part of the same network that began in 1911, still step outside on clear nights, find Orion, and add one more data point to a data set now well over a century long. At the European Southern Observatory's Very Large Telescope, high in the Atacama Desert of Chile, instruments capable of resolving surface detail across hundreds of light years remain periodically pointed toward Betelgeuse, tracking the slow drift of its giant convection cells and the faint, dusty plumes it continues to shed into space. At the Atacama Large Millimeter Array, only a short distance away, a different set of instruments listens for the star's emissions at wavelengths invisible to the human eye entirely, mapping the cooler, more distant material Betelgeuse shed centuries and millennia ago. Together, these observatories, and dozens of others like them, form a continuous overlapping web of attention, watching a single star from angles and wavelengths no single instrument, however powerful, could achieve alone. Ordinary observers contribute to this same effort in smaller but genuine ways. Simple mobile applications now let amateur astronomers log brightness estimates directly from a backyard or balcony, feeding observations into the same international databases used by professional researchers. A retiree in Ohio, a teenager in rural Australia, and a hobbyist in the Netherlands might each, on the very same night, look up at the same reddish point of light and quietly add their own small piece to a collective record that has by now spanned more than 11 decades without interruption. Space-based observatories add their own layer to this ongoing effort. The Hubble Space Telescope, now well into its 4th decade of operation, periodically revisits Betelgeuse to track its slowly recovering atmosphere and the faint wake of disturbed gas left by its orbiting companion. The James Webb Space Telescope, launched decades after Hubble, contributes infrared observations capable of tracing cooler material invisible to optical instruments, extending the same patient, decades-long record into wavelengths earlier generations of astronomers could never have accessed at all. Nothing about tonight's observation will look any different from any other night this year. The star will appear steady, reddish, and calm, precisely as it has appeared for as long as written human history extends. Whatever is happening deep inside its core remains, as it always has, completely invisible from the outside. That quiet, ordinary appearance is, in its own way, remarkable. A star capable of producing one of the most violent events in the universe looks, from Earth, indistinguishable from any other point of light in the winter sky. On a clear night, away from the brightest city lights, Orion remains one of the easiest constellations to find anywhere in the world, its three-star belt cutting a straight, unmistakable line across the sky. Betelgeuse sits at the upper left corner of that familiar shape, its reddish color noticeably different from the blue-white stars surrounding it, exactly as countless observers, across thousands of years and dozens of civilizations, once noticed with nothing more than their own eyes. From the northern hemisphere, Orion rises in the eastern sky during the autumn months, climbs high overhead through the depths of winter, and gradually sinks toward the west as spring approaches, a slow seasonal drift that has repeated, uninterrupted, for as long as human beings have been watching the sky. For much of the southern hemisphere, the same constellation appears upside down relative to how it looks in the north, Orion's hunter figure seemingly standing on his head, a small reminder that the sky itself looks different depending on where, on this one small planet, a person happens to be standing. Wherever it is viewed from, and in whichever orientation, the light reaching an observer's eyes tonight left Betelgeuse 548 years ago, crossing an almost unimaginable distance of empty space at the fixed, unchanging speed of light, arriving finally tonight as a single, quiet point of reddish color above the horizon. That light asks for nothing. It does not need to be understood, or tracked, or explained to continue arriving night after night the way it always has. 548 light years, 16 to 19 times the mass of the Sun, a radius so large it would swallow Mars and perhaps Jupiter besides. A core no wider than the Earth, holding, for now, steady against its own enormous weight. A quiet 6-year companion tracing its patient orbit through the giant's outer atmosphere. Numbers, all of them, real, measured, and settled, at least for tonight, into something calm enough to rest inside. The Milky Way galaxy contains somewhere between 200 and 400 billion stars, and only a small fraction of them, likely fewer than 1 in every 10,000, are massive enough to ever become red supergiants at all. Astronomers currently catalog only a few hundred confirmed red supergiants across the entire galaxy, scattered so far apart and so often hidden behind vast clouds of interstellar dust that most remain far too faint to see without a telescope. Betelgeuse is a genuine rarity, close enough, bright enough, and unobscured enough to be studied from Earth in this much detail, a fortunate accident of distance and geometry that has turned one ordinary dying star into the single best-studied example of this entire, uncommon category anywhere in the sky. Somewhere else in the galaxy, right now, Other stars are almost certainly moving through this same late stage of life, quietly, invisibly, far too distant or too obscured for anyone on Earth to ever notice. In, hem/out. There is no urgency in this. Betelgeuse has burned for millions of years already, and whatever remains of its life will likely stretch across many thousands more, an almost incomprehensible span of time by any human measure. Even the more cautious estimates, the ones suggesting the star may already be closer to its final stages than once believed, still describe a window measured in tens of thousands of years, not days, not years, not even centuries. Every generation of astronomers who has studied this star, from the earliest naked-eye observers in ancient Egypt and Babylon, through Herschel, through Pease and Michelson, through Dupree and Howell, has looked up at the exact same steady, reddish light that remains visible tonight. To put that span in perspective, tens of thousands of years is longer than the entire span of recorded human writing, longer than the domestication of wheat, longer than the earliest cave paintings in France and Indonesia. Whatever changes are unfolding inside Betelgeuse's core, they are unfolding on a clock utterly indifferent to the pace of a single human life, or a single human civilization, or, most likely, several civilizations yet to exist. Nothing about tonight requires action, or worry, or watching the sky for signs. The star is simply there, doing what it has always done, exactly as it will continue to do for longer than any of us will be here to notice. Winter will end, as it always does, and Orion will slip below the western horizon for another season, giving way to the stars of spring and summer. It will return again in autumn, rising in the east exactly where it always rises, Betelgeuse still marking the same shoulder, still holding the same quiet color, indifferent to how many winters have passed since anyone last checked. This has happened every year for as long as Earth has kept its current tilt and orbit, and it will keep happening for a very long time still, entirely independent of whatever slow countdown continues, unseen, inside the star itself. Betelgeuse, at least, is not entirely alone in this. Somewhere in its own extended turbulent atmosphere, tracing a slow 6-year orbit, its small companion Siwara continues circling, patient and quiet, passing again and again through the outer edges of a star many times its size. Neither star seems concerned with the other's schedule. Each simply continues along the path gravity has set for it, exactly as it has for as long as the pairing has existed. This story has traveled a long way to arrive here. It began with a single point of reddish light in an ancient hunter's shoulder, noticed independently by civilizations that never once made contact with each other. Greek shepherds, Egyptian priests, Chinese court astronomers, and Aboriginal Australian skywatchers, separated by oceans and thousands of years, each looked up and saw the same reddish point of light, and each, in their own language, gave it a place in a story about a hunter, a deer, a shepherd, a shoulder. It moved through careful centuries of measurement, mirrors and light waves, revealing a size too large for ordinary intuition to hold. Pease and Michelson, working with nothing more than mirrors and careful mathematics, first proved that this single point of light was, in physical fact, larger than the orbit of Mars. It descended into a core no telescope will ever see directly, tracing fusion through element after element until nothing remained but iron and silence, hydrogen, helium, carbon, neon, oxygen, silicon, each stage faster than the one before it, each one a countdown running quietly, invisibly, far beneath everything visible from Earth. It followed that silence into collapse, into a burst of nearly invisible particles racing ahead of light itself, into a shockwave stalling and reviving and finally breaking free. 99% of the entire event's energy carried away in seconds by particles that passed through solid matter as though it were not there at all. And it surfaced again in the careful, patient records of court astronomers, a Danish nobleman, a German mathematician, each looking up at exactly this kind of ending without knowing yet what they were truly seeing. Their careful notes outliving them by centuries, waiting patiently for instruments capable of finally explaining what they had witnessed. It reached forward into the modern era too, into a photographic plate in Chile in 1987, into 3 detectors on 3 continents, registering the same brief burst of particles within seconds of each other, into rings of glowing gas still colliding, slowly decades later. And it reached, more quietly still, into a faint star catalogued in 1680 that simply vanished from the sky, unnoticed, its true nature understood only centuries afterward. It reached back even further than that, into a court record from the year 185, into a fading light over Centaurus that a handful of observers in Han Dynasty China thought worth writing down, never imagining that record would still be read and still matter more than 1800 years later. Each of these accounts, separated by centuries and continents, describes the exact same fundamental event, a massive star reaching the end of a process that tonight has been traced from its first fusion of hydrogen to its final silent collapse. Astronomers will keep watching, the data will keep accumulating, and somewhere in that vast, patient timeline, long after tonight, the story now told across this recording will eventually reach its conclusion, quietly the way it always does, and be witnessed by someone the way it always has been. Even now, Betelgeuse itself keeps a kind of rhythm, expanding and contracting in a slow 400-day cycle, swelling gently outward, then settling back over and over, a vast, unhurried pulse repeating across more than a year at a time. It is not a heartbeat in any literal sense, but the comparison is difficult to resist. A rhythm this patient, this steady, sustained across millions of years, older than any single human life could measure. Layered on top of that shorter rhythm sits the slower, nearly 6-year drift now understood to trace Sawarha's own orbit, one massive body and one smaller one, circling each other in the dark, indifferent to the sequence of collapse quietly building at the larger star's center. 2 rhythms, one fast and one slow, both playing out simultaneously, both utterly unconcerned with anything happening on the small, distant planet currently listening to them. For now, the sky stays calm. Somewhere tonight, in dozens of languages, under dozens of different names, someone else is looking at this exact same star. In Cairo, where ancient priests once linked it to Osiris. In Beijing, where court astronomers once tracked it alongside the lunar lodge called Shen. In Sydney, where it appears upside down, still marking the shoulder of a hunter chasing prey across an unfamiliar southern sky. In a small town somewhere in India, where a much older tradition once called the surrounding stars Mistriga, a wounded deer forever fleeing across the heavens. In a quiet backyard in the American Midwest, where a retiree logs one more brightness estimate before heading inside for the night, adding a single data point to a chain of observation stretching back more than a century. None of them, right now, are thinking about neutronization or binding energy curves or the Chandrasekhar limit, Most are simply glancing upward for a moment at a familiar reddish point of light, the way people have for as long as there have been people to look. That simple act, unremarkable as it feels, connects directly back to everything explained across this entire story. The star does not require anyone to understand its physics in order to keep shining patiently exactly as it always has. The reddish light continues arriving, patient and unhurried, exactly as it has for over 5 centuries. In, multi out. Everything you heard tonight is real. Betelgeuse is out there right now. If tonight's story helped you drift off, the best thing you can do is subscribe, so more of these science stories can keep finding their way to you. A like helps more than you might think, and turning on notifications means you will not miss the next one. Sleep well. Rest easy under the same quiet sky that has held this story for over 500 years. Good night.